Tensees, here we are with our last lesson of the linear relations and functions unit. What we're going to look at is a lot of examples that tie in to applications of relations, like it says, and basically understanding that when we have a graph of something, all this information we've talked about is important, and putting it all together. So this is lesson 7 and 8 together because it's all the same information. Lots of examples, so let's get through them and see how all this ties together in the big picture. So if we take a look first at page 33, we have a situation where there's the cost of pizza and what it costs depending upon the number of toppings. So we want to first of all graph the situation. Well, our table of values for this situation, well, it could also be presented in a graph, and it's giving us our ordered pairs. 0, 12, 1 topping means it's $12.75, and so on. So we have our X and Y values. Let's graph it. So there's the graphed information. Those are the points that tell us if we label this. This is number of toppings, and our y-axis is the cost, because toppings change independently and cost is dependent on the number of toppings. There's our independent dependent variable. Do I want to connect the dots? In this case, I don't. This is discrete data, and that's important because I don't purchase part of a topping. I buy a topping, 1 topping, which is going to take the price to $12.75. I buy a second topping, which takes the price to $13.50. I don't buy parts of toppings, so it's discrete data we have to graph with dots. Second part, what's the pattern we see in the table? Well, there's a pattern that takes all of the X values, independent values, to each other. What are we doing? We're adding 1 in every situation. We've increased by 1. Well, is there a pattern? It doesn't have to be the same plus 1, but do I see a pattern with my dependents? Every price is going up by 75 cents. So what's the pattern that I see in the table? Well, if I increase by 1 topping, we increase the cost by 75 cents. So because we're increasing by 1 topping and increasing by 75 cents every time, well, there's the relation. And we can see that that relation happens on the graph as well. If I start with my first point and I add 1 topping, well, I've gone up 75 cents. And if I add a second topping, I've gone up by 75 cents. So the pattern that we see on the table of values has to be the same pattern that we see on our graph. That's important. The pattern on the, because it's a relation, the pattern on the table of values should match the pattern on the graph, because these are just 2 different ways of showing the same thing. Well, with that being said, we can create a function for the situation. Remember, a function is just another form of an equation. So what's the equation for this? Well, we have to come up with, how do we get the cost of the pizza? Well, we can see, or hopefully we can see, that without any toppings, it's $12. So it doesn't matter if you get toppings on, you're going to have an initial cost of $12. That's for the dough, the cheese, the sauce, no toppings. It's still $12. But we're then going to increase 75 cents for every topping. So that is not yet our answer for C, because that's an equation. Remember, an equation is two variables. We want the function for the situation. So a function says we want the cost based on the number of toppings. That's the only change I need to make to take an equation to a function. And there's the function. The cost based on the number of toppings is $12 plus 75 cents per topping. So there you go. There's three ways that we can present the same information. Table of values to a graph, and we can see the relation there, and then we can create an equation or a function for that same situation. Now, D says from the table, how can you tell it's a linear function? Well, I don't want to just focus on from the table. We know things are linear functions for a bunch of different reasons. So, I know there's no room in the booklet, but it's important to jot this down. You have a linear relation if the first thing in your table of values, this is important information. If the table of values has a pattern for the X values and the Y values. And we just talked about that 2 minutes ago. We saw that X is going up by 1. If I see a pattern in my X values and a pattern in my Y values, now the two patterns don't have to be the same, but I have to see a pattern. We end up with a linear function. How do we know it's linear? Well, again, I showed. X goes up by $1 or one topping, we go up by 75 cents. Go up by one topping, increase by 75 cents. And that creates the linear relation. So that's one way to identify if you have a linear relation. Table of values has a pattern for the X and Y values. Second thing is the graph itself. Well, this one's kind of a no-brainer if we go back. How did we know that this was a linear relation? Well, because our points, even though it was discrete data, we see they still go up in a line because of that relation with the table of values. So we know we have a linear relation if the graph creates a straight graph. It's that simple. Whether it's discrete or continuous, it's still going to be straight. Now from there, the other thing we can do is we can look at the equation or the function that gets created. Now this one is not as straightforward and will make sense to you as you go on in math, but we know we have a linear relation if the largest exponent in the equation or function is 1. So if the largest exponent is a 1, we know we have a linear relation. And if we take a look over here at our function and our equation, our t has an exponent of 1 there. It's not written in, but it's assumed to be there. So because of that, when it's just a t or an x or a b or whatever with an exponent 1, we know we have a linear relation. So those are three things that will help us moving forward to know if we have a linear relation. So let's take a look at page 35 real quick. With that information, stop the video and quickly take a look. A, B, C, D, the examples. E, F is all I went to, I believe. A, B, C, D, E, F is enough. Take a look at A, B, C, D, E, F, and then decide if they're linear or nonlinear and explain why. Give it a try, and then we'll talk together. Well, here we go. A, y equals x plus 32. We have an equation. What's the exponent on the y? A 1. What's the exponent on the x? A 1. An exponent of 1 tells us that it's linear. C, ordered pairs. Well, we didn't really have a rule for ordered pairs. But what I like to do is understand that other forms can give us the same information. Our first point is 0, 0, negative 2, 0, 1, 0, 4, 0, 7, 0. So with that, here, do we see a pattern consistent in our x values? There's no pattern existing. Yet we have a pattern here of increasing by 0. So this is not linear. The other thing we could do with ordered pairs is we could just graph it quickly. We have 0, 0, even if it's not perfect. We have negative 2, 0. We have 1, 0. We have 4, 0. We have 7, 0. Oh, wait a second. We have to be careful sometimes. That is linear because of the graph. The reason it doesn't work in our table of values is technically I could fill in the blanks. What's this showing? That every y is 0. So I could fill in the blanks for my x's. I start at negative 2, my smallest value. It's a 0. Everything is a 0, so that means negative 1 would be 0. 0 would be 0. 1 would be 0. 2 would be 0. 3 would be 0. 4 would be 0. So technically, I have to think a little bit with that one. Sometimes, if it's not in the right form, we want to check it. So in this case, it is linear. Got to be careful. Look at it from different perspective if it's not always obvious. From there, we can go to B and D. Sorry, I went in a little bit different order, but that's okay. B, table of values. Do we have a pattern in our x's? Yes, we're going up by 1. Do we have a pattern in our y's? We're going up by 3, up by 5, up by 7. Definitely no pattern. These aren't zeros, which are a unique situation. In this case, definitely not linear. And we could see if we graphed it quickly. Again, if we took a quick look at the graph. 1, 1 would be there. 2, 4 would be a little higher. 3, 9 would be higher. We can see that's definitely not linear. Which takes us to D. There's the graph. It's not linear, so no brainer, not linear in that case, using the rules and the knowledge. E and F. E and F, here's an equation. What do we notice right away? We notice that we have an exponent of 2. And we can only have exponent 1s for linear. So because of that exponent 2, it's not linear. Here, our x has an exponent 1, y has an exponent 1. Exponent 1 tells us it's linear. So there, to add linear, when is it linear? How do we know? Different ways we can check if our relations are linear. Now that takes us, back to page 34, but rates of change. Now our rate of change is something we're talking about now, but we're also going to use moving forward. Rate of change is how one quantity changes in relation to another. Now, there are 3 different situations. A constant rate of change, which we see is linear. If we have a linear, we can calculate the rate of change for a linear situation. And we calculate it by doing the change, which is what a triangle means in math, change in our dependent variables over change in our independent variables. And we'll look at that a little bit moving forward, but that's rate of change. This calculation works for a linear situation. Because what it's saying is linear because as I make a change horizontally, I make a change vertically. But I would make the same change horizontally, same change vertically, and I keep ending up on the line. Same change horizontally, same change vertically. When my changes horizontally and vertically are the same, we end up with a line. So we can calculate a rate of change for a linear, constant rate of change. But not all rate of change is the same. It's possible that all of a sudden something changes a lot and then it changes very little. We saw that in our graphing stories. It's not always going to be identical. Same thing on our graphing stories. Sometimes there is no rate of change. As we go on, nothing's happening. It's just staying the same, so no rate of change. So rate of change, change in our dependent over change in our independent when we have a linear rate of change or a constant rate of change, which we'll look at moving forward. So rates of change, let's take a look at these examples on page 34. Would it be a constant rate of change, non-constant, or no rate of change? If a car is driving down the highway, if you're driving down the highway, which means chances are you might have cruise control on, so it's very constant. This would be a constant rate of change. And the reason being, you set the cruise control so that you're driving, in this case, I don't know, let's say you're going the speed limit, which of course depends upon which road you're on, not everyone does. You're going 110 kilometers for every hour. So that means in the first hour, you've probably traveled 110 kilometers. In the fifth hour, not over the 5 hours, but in that fifth hour, if you're doing 110 kilometers per hour, in the fifth hour, you'd go 110 kilometers. It's a constant rate of change. Now, sometimes, obviously, you have to speed up or slow down if something's on the road. But honestly, driving down the highway, it's constant. Whereas a bus, if we take a look at B, if a bus pulls away from the curb, what's the bus doing as it pulls away from the curb? It's accelerating. And accelerating means it's not constant. The speed it's going initially, it has to get up to speed, which means it's not constant at that time. A sprinter running a 100-meter race, is that a constant rate of change? It's not. Again, the idea of accelerating. I'm not a sprinter, so I don't know exactly how long it takes, but we could say there's a constant rate of change. If I were to graph it for a sprinter, over a short period of time, a sprinter gets up to speed. And then from there, they maintain that speed throughout the race. So in that first, 20 meters, they're accelerating. So the first bit of time, and then after that first bit of time, which was a quick, now it goes more constant. So this could be a constant rate of change, but because of this change, it's not constant. So again, not constant throughout the race. Parts of the race will be constant, but not initially. A cockroach population doubling every 12 hours. Well, doubling every 12 hours does not mean constant rate of change. Constant rate of change would mean first hour, they're increasing by 12. Constant rate of change would mean second hour, they've increased by 12. But they haven't. If they double every 12 hours, The first 12 hours, it goes up by 12. Sorry, not 12. Let's say we started with 10 cockroaches. In the first hour, the first 12 hours, those 10 cockroaches doubled to become 20. In the second hour, or 12 hours, because they doubled, the 20 become 40. In the third 12 hours, if they double, that becomes 80. So we see they double to 20, but then they double and get 40 more. Then they double and get 40 more. It's not constant. So this is not constant, because if it was constant, let me go back again. If we started with 12 the first hour, or if we started with 10, sorry, the first hour there would be 10 more. The second hour, there would be 10 more to 20. The third 12-hour time, it would 10 more to 30. But it doesn't do that. Because it's doubling, the 10 become 20, the 20 become 40. It's not a consistent rate of change, so it's not constant. And E, money earned compared to hours worked, well, this would be constant rate of change. Because that first hour, you make $15 per hour. That second hour, you make $15 per hour. In that seventh hour of your shift, you're making $15 per hour. It's a constant rate of change because it's the same amount for a set time. Difference between constant and not constant. Linear versus not linear. Take a look at another example if we go to page 36. Now on page 36, we have an example where it talks about a car rental is $60 right away, $60 before you pull off the lot, and then $20 for every 100 kilometers that you drive. We can see this as a linear relation in different ways. Well, the table of values is there. How do we know it's linear? Well, if we take a look, what's happening in that table of values? Our X value, the distance you drive, is increasing by 100, and what happens to the cost each time? Well, the cost is going up by 20. So we see a consistent pattern occurring for our distance increased by 100 kilometers, results in the cost increasing by $20. Table of values has consistent patterns. If we graph this, well, at distance 0, because here's our distance and here's the cost, because cost depends on that independent distance. If we drive 0 distance, we're going to have 20, 40, a $60 cost. But if we drive 100 kilometers, so if I go up 100 kilometers, what happens to the price? Well, it goes up by 20. And if I drive another 100 kilometers, what happens? The price goes up by 20 again. So we can see that we end up with a linear relation because this increase of 100 kilometers results in an increase of $20. Increase of the next 100 would be an increase of $20 again. So we have a linear relation on that graph if we were to graph it. The rate of change. Well, here, rate of change, remember, we talked about it, haven't looked at it yet with calculations, but the rate of change is the change in our, what was it? Independent or Y values goes over the change in our change in our dependent Y values goes over change in our independent X values. Well, what was the change in our Y values? We see the cost went up by 20. And what was the change in our X values? We see it was a change of 100. So what's the rate of change here? Well, let's also include units because units are important here. It was a $20 change for every 100 kilometers. Well, if I divide these two values so that I can get a decimal, 20 divided by 100, that gives me 0.2. But what are my units? Dollars compared to kilometers. Well, dollars, let's go 2 decimal places. If you're paying $20 for 100 kilometers, well, that works out to be 20 cents for every kilometer. And there's your rate of change. The change in your dependent over change in independent. Divide them and you get 20 cents per kilometer. So every time you drive a kilometer, it's 20 more cents. Drive a kilometer, 20 more cents. Drive the 75th kilometer, that was 20 cents. The 482nd kilometer, that was 20 cents. It's a constant change of 20 cents for every kilometer. So we can put that into an equation. What's the total cost to rent the car? You have that initial cost of $60 plus the rate of change, which was 20 cents for every kilometer driven. $60 plus 20 cents times the kilometers driven, because that's your rate of change. And why do we have a rate of change? Because it's linear. When we look at our equation and our variables, exponent of 1, biggest exponent is 1, tells us it's linear. So this graphing, the relationship between the different forms, all makes sense. It all ties together brilliantly. Page 37. Are the relations linear? We've just talked about it. And if they're linear, what else would we know? Is there a constant rate of change? That's what we're looking to identify. So stop the video, take a quick look, A, B, D, and E, and then we'll talk. Here we go with A. What's the change in our x's? -9, -7, -5, -3, -1, we're going up by 2. What's the change in our y's? -10, -5, 0, 5, 10, we're going up by 5s. So constant change in our x, constant change in our y, definitely going to be linear. Take a look at that graph for the amount of radioactive isotope. It's a graph. It's not straight, not linear. So it's not a consistent rate of change either. If you talk about a dog sled that moves at an average speed of 10 kilometers per hour, average speed means that's what it's doing. Every hour it goes 10 kilometers. In the first hour it goes 10 kilometers. In the third hour it goes 10 kilometers. In the 15th hour it goes 10 kilometers. So it's going to be linear because it has a constant rate of change. Those two are related. If you have a constant rate of change, it's going to be linear. And E, the area of a square is related to the side length. Well, the area of a square, in terms of side length, we know area of a square is side squared. Well, right away, there's our equation. What do I see? I see an exponent bigger than 1. So it's not linear. There's what we're looking at, relation between linear and rate of change. All of the pieces in this unit tie together. Page 38. Let's look at a bunch of examples in terms of word problems. So page 38. We have hot tub that has 1,600 liters of water. Graph A, it's being filled so that we can see over time the volume of water goes up. Volume is increasing as time goes on, so it's filling. Different situation in B, because we see that as time goes on, our volume is actually starting high, but over time it goes down. So that's why if volume's going down, we're draining the tub. It's being emptied. So let's take a look at what it has to say. Identify the dependent and independent variables. Remember, dependent variables are the x-axis variables. And in this case, it's time and time. So they're both the same. Dependent is time in both cases because that's what's changing or being manipulated to start. And the independent variable, remember, is always your y-axis. And the y-axis is volume and volume. Because the volume of water, I changed the wording, messing this up, I apologize. Independent is our x-axis. Dependent is our y-axis. Independent is x, sorry. Oh, messing up my terminology here. Dependent is the y. Because time changes on its own, but what's the dependent variable? In both cases, it's the volume of water. And the volume of water that remains is dependent on how long the tap or the drain's been open. So independent is time, but how much water remains depends on how long it's been filling or emptying. Second part to that is calculate the rate of change for each relation. So we said, and we've looked at it once, but again, rate of change is the change in our y dependent values over the change in x, which are our independent. So we need to find 2 points on the graph that's easy to identify. You can choose any 2 points that you want. So for graph A, just for simplicity's sake, I'm going to pick a couple points that are easy to read the values. So for graph A, the rate of change in the y's over change in x. Well, let's take a look. If I want to go from that point to that point, what's the change in my y values? I take a look. We went from 400 up to 1200. That's a change of 800. So 800 liters are changing over the change in our x values. Well, we're going from here, which is 20, to here, which is 60. So 20 to 60 is a change in 40 minutes. So we talked about 800 liters every 40 minutes is the change. Let's put that into terms that are a little easier to work with. If I do 800 divided by 40, what do I get? I get 20. And that's 20 liters per minute. That's the rate that it's filling at. 20 liters per minute. But just as a second check here, let's take a look at 2 other points. Whatever 2 points you want to use. Let's go here and let's go up here. We should have the same rate of change. Let's check if that's true. Change in y. What's the change in y? Well, here we're going from, I just can't quite read, that's 600 to 1600. Well, what's the change in our y? 600 to 1600? Well, that's a change of 1,000. And what's the change in our x values? Well, we're going from 30 to 80. And 30 to 80, that's a change of 50. So 1,000 liters every 50 minutes. Second way to calculate it. If I divide 1,000 by 50, what do we get? 20 liters per minute. So we just need to find 2 points on a graph, identify change in our y over change in our x. And that tells us, in this case, 20 liters are filling every minute. Now graph B, a little bit different though. We have to be careful here. Rate of change in y over change in x. So I'm just going to pick two nice and easy points here. What's the change in our y? Well, we have to be careful because initially for this one, the rate of change here, what's the change in y? We're not going from 0 to 1600. We're as high as 1600 and going down to 0. So this is a negative change. From 1600 to 0, a negative 1,600 liter change. And it's negative because the volume's going down because we're emptying the hot tub. And what's the x change? We're going from 0 to 40. But that is in a positive direction. Here we start at the 0, we go to the 40, so it's 40 minutes. So in this case, if I put this into an easier situation, divide my 1600 by 40, we end up with negative 40 liters per minute, which makes sense. It's negative because it's empty. So there's the rate that it empties at. What do we notice? It's losing 40 liters per minute when emptying, but only getting 20 liters per minute when filling. So it empties quicker because the rate of change tells us that. It's also maybe why this graph is steeper than this graph, because it's emptying quicker. So rate of change, we can get important information from a linear graph using the rate of change. C here tells us we want the domain and range for each. Well, domain and range is telling us where we're starting and stopping. So for this first graph, well, we take a look at the graph. We want the domain. Remember, domain is what part of the x-axis is being utilized. Our left wall is at 0. Our right wall goes as high as 80. So I want to write the domain going from 0 to 80. Well, two ways to do it. Set notation, fancy brackets. We want the x value such that because there's two endpoints, 0 is less than or equal to x, which is less than or equal to 80. And it is a member of the reals because we have every bit of time. The domain is describing the time. So what does this tell us? That it's going anywhere from 0 to 80 minutes. That's how long you can fill for. You can't fill longer than 80 minutes because at 80 minutes, well, obviously it's a 1,600 liter tub. After 80 minutes, it overflows. You really don't want to go beyond 80. If we do range, range is our y-axis. Well, the range is going from our floor, which is at 0, up to our ceiling, which is 1,600. So again, two endpoints. We want y such that 0 is less than or equal to y, which is less than or equal to 1,600. And y is a member of the reals. There's your domain and range. Graph B, same idea, domain and range. Domain, what part of the x-axis is being utilized? From 0 to 40. So for our domain, we want the x value such that 0 is less than or equal to x, which is less than or equal to 40, and x is a member of the reals. The range, we're as high as 1,600, we're as low as 0. Domain and range doesn't matter order. Here, we just want the y value such that our low value of 0 is less than or equal to y, which is less than or equal to 1,600. And y is a member of the reals. All it tells us is how much is being utilized. Range is the volume. So we know with our range, we're saying the volume could be anywhere from 0 to 1,600. Y is greater than or equal to 0, but y is less than or equal to 1,600. So this tells us the volume of water is from 0 to 1,600. So domain and range in a real life situation can actually give us information that's useful. Page 39 take a look at the float plane. Yes, this says now less than 8, but it's all the same stuff, so let's get through it. 39. Float planes fly into remote lakes. The graph is the height of the plane as it descends. So where does the graph intersect the vertical axis? What does it represent? So we've talked x and y axes, x and y intercepts. We want to know the vertical, so up and down. So this is really asking for the y-intercept. But just because we've talked about y-intercepts doesn't mean it's nothing. The y-intercept is an important piece of information. There's our y-intercept. Where does it occur at? It occurs at 0, 1,000. But what does that tell us? Well, our x is time versus height. So we know at time 0, before it starts to descend, it's 1,000 meters. So what does the y-intercept represent? It's talking about the maximum height flying, because it descends from that height. So the y-intercept is telling us, hey, here's the maximum flying height. Where does the graph intersect the horizontal axis? So the horizontal axis would be the x-intercept. And again, where's our x-intercept at? It's at 10, 0. X is 10 when y is 0. So this now is telling us 10 minutes for a height, because y is a height, 10 minutes for height 0. So what does that represent? That's telling us 10 minutes to fully descend and land. So x and y intercept aren't just math things. They are math things, but they have purpose, especially when you have a real life situation. Still going with this. What's the rate of change for this graph? Rate of change. Let's make sure I don't mess up my terminology this time. Rate of change is the change in our y, or dependent over change in x, our independent. So pick 2 points on there. Any 2 points you want. I'm going to pick those 2 points. And I want to know, how do I change vertically going from point to point? Well, I'm going from 800 down to 400. That's a negative 400 meters, because that's what our dependent represents, meters, height. And what's the change in the x? Change in x is going from here to here. It's going from 2 to 6 minutes. Well, 2 to 6 is 4 minutes. So let's now put this, after we divide, negative 400 divided by 4 is telling us negative 100 meters per minute. Why is it negative? Because the plane is going down. The plane is going negative 100 meters every minute. So every minute it drops down 100 meters. Rate of change. What are the domain and range for this graph? Well, domain, we're going from 0 to 10, 2 endpoints. So our domain would be x values such that if we're going from 0 as a low point to 100, 0 is less than or equal to x, which is less than or equal to 100, but x is a member of the reals, and not 100, but 10. So sorry. Less than or equal to 10. X is a member of the reals. Well, domain is time, so this is telling us our time is anywhere from 0 to 10 minutes to land. And the range, the y values being utilized. Well, our y values, our floor is as low as 0, but our ceiling is 1,000. So we want the y value such that small value less than or equal to y, less than or equal to 1,000. And y is a member of the reals. So all of this information we've talked about fits together for linear relations. Page 40, a couple more examples. Make sure there's a solid understanding. Page 40, sketch a graph of different rates of change. Well, what have we seen about positive rate of change? It's when our graph is going in an upward direction to the right. That's a positive rate of change. What could it be? We've looked at all kinds of things. Time and elevation possibly. Over time, you go up for a plane taking off. That could be a positive rate of change. As time goes on, the plane goes up. Negative rate of change is showing us that our line is going down as we move to the right. What could that be? Time and all kinds of different things we could put in there. Let's talk about the temperature. If you have a cup of hot cocoa or tea or coffee, over time we start at a high temperature and it drops in temperature consistently. Negative rate of change. And we're going to work a lot more with this as we move forward to the next unit. Here we have a graph showing the height of a burning candle. So write the coordinates of where the graph hits the x and y axes and describe what these represent. Well, x-intercept is where we hit the x-axis. And our x-intercept occurs at 45. Well, what does that represent? It's a 45-0. There's our x-intercept. Well, what does the x represent? It's minutes. What does the y represent? It's how long the candle is. So what does the x-intercept tell us? That after 45 minutes, the candle has burned down completely. The x-intercept has an important piece of information. It's where the candle is now completely burned. Where if we do the y-intercept is where we hit the the y-axis, which is at 9. So our y-intercept is when x is 0, y is 9. And again, x independent is time, minutes, and dependent is centimeters. So what is that telling us? It's telling us that the candle is 9 centimeters long at the start of the burn. You have a 9 centimeter long candle because you haven't started burning it yet. That's how long the candle is when it starts. X and Y intercepts have important meanings. What again are the domain and range of this function? Well, domain. Domain, x-axis, 0 up to 45. So 0 to 45, well, I'm going to do something a little different this time. Low value is 0, high value is 45. Both of them occur, so we use the closed brackets. There's our interval notation for domain and range. The range, y-axis, it's going from as high as 9 down to as low as 0. So 0 and 9, and they're both part of distinct graphs. So in set notation, the range is 0, 9, square brackets. Different ways to look at domain and range. Page 41. Which graph has a rate of change in -5 and a vertical intercept of 100? Well, vertical intercept is just our y-intercept. Well, if we take a look at the first graph, y-intercept is 100, 0, 100. Second graph, y-intercept is also 100. So this piece of information doesn't help us. But a rate of change of -5. What does the negative tell us? It tells us that it's going down. So the only possible solution there is the one that's going down. That has a positive rate of change. So this one we would have to assume is a negative rate of change. So let's do a quick check. Rate of change, pick 2 points. 1 point, 2 points, nice and obvious. Rate of change is our vertical change. Here, I'm going from 75 down to 25. My rate of change, because we're going down from point to point, 75 to 25 would be negative 50. And what's the horizontal change? We're going from 5 to 15, which is 10. Negative 5 divided by 10 is negative 5. And in this case, does it tell us specifically what we're looking at? It's really hard to read because it's a small graph. So we have a rate of change of negative 5. Page 41, sketch a graph, linear function, f of x equals 4x minus 3. Use x and y intercepts or a table of values, or maybe a combination of both. Well, f of x is the same as saying y equals 4x minus 3. If I want my x-intercept, what's important? Y has to equal 0. I've talked about it quite a bit already. So if y equals 0 for 4x minus 3, add 3, 3 equals 4x, divide by 4, x is 3/4. So x is 3/4 when y is 0. There's my x-intercept. 3/4, 0. So not quite at 1. My y-intercept, well, my y-intercept is when, if I want the y-intercept, x is 0. So we know we'll have a y value if I use 0 for x. 4 times 0 is 0. So y is negative 3. So that means our intercept, when x is 0, y is negative 3. So there's my second point. So I can now create that graph. And if I choose to, I can maybe choose another point or two. Now, am I going to be able to choose a point? We can see it's not going through every absolute perfect intersection. So I'm going to try, maybe for this one, using x at 2. I see it should be close to 6. 2 should be really close to 6. Maybe it'll be 6 exactly. So I'm going to now use a table of values. If x is 2, 4 times 2 minus 3, y equals 6 minus 3, which is 3. So when x is 2, y is 3. That didn't work at all. Oh, 8. 4 times 2 is 8 minus 3, which is 5. Sorry. Oh, lots of little errors today. 2 and 5. So 2 and 5, well, we're in the ballpark. It might not be absolutely perfect because that's an estimate, but at least we're in the close range. So it's acceptable. 41. Last example, the electrician charges $190 to complete a job. Use the graph to determine. So our graph can give us lots of information. What's the automatic cost to make the house call? No work is being done. So no work has been accomplished, so time is 0. We see we're going up by intervals of 60 here. So we can see it's $60 to show up and not do any work. Automatic cost. Hourly rate for the electrician. Hourly rate, what is that? That's the rate of change that we've been talking about. How much in the first hour will be the same they charge for the 4th hour, which would be the same for the 5th hour. So to get rate of change, again, rate of change is the change in our dependent over the change in our independent. And it's given us 2 points. So what's the change in our y? Well, we see we're going from 180 up to 300. So that's a change of 120. And that, we can see that y is dollars. And to go from this point to this point, our change on our independent is going from 3 to 6, which is a total of a change of 3. So it's $120 for every 3 hours of work. Let's divide those, and what do we get? 120 divided by 3 is 40, which is dollars per hour. So there's your hourly rate, which is just your rate of change. And for C, using the graph, it says the number of hours the electrician worked for $190. Well, what we want to do is, first of all, just get rid of a little bit of those sketches so it's easier to see. We want to know the number of hours for the $190. Well, first we need to figure out where $190 occurs. There's 180. So 190 would be a little bit above that. So if we want to use our graph, the number of hours we need to figure out on the bottom. So $190 takes us to that point on the graph, which takes us down to there. Well, there's 2 hours, there's 3 hours, it's 3 and a bit. So it would be about 3.5 hours of work. So we can use the graph because the graph gives us information. All of this is related. Lots of examples, lots of things to think about, but more importantly, lots to practice. Yeah, this is a big assignment. Lots of questions, but there's not a lot of calculations. But understanding how all this fits together. The only way to get good at it is to practice it. So do it. Bring all of this information we've talked about for all of linear relations and functions. It's all coming together in this assignment. Practice it. Make sure you understand it. Have fun.